Okay. All right. So here we're going to continue here and build on this concept of the norm and the inner product. All right. So now we're going to look at properties that arise from excuse me, the inner product for particular sets of vectors. Right. So we'll define this idea of orthogonal, right, which we are more used to hearing or being described as a term as perpendicular, right? So being orthogonal means for vectors u and v, they are orthogonal if the vector u, the vector v is equal to 0. Okay, now a good way to think of this, the geometry of it, is if we think in R2, right, the unit vector, the standard vector 1, 0, and then the one in this direction here 0, 1, right? Call this one my u, this one my v, right? So when I take, these should be, okay, so the inner product of u, here, let me use the notation we've been using in class here. So when I take the inner product here of u and v, we get, so 0 times 1 plus 1 times 0, and we get 0. All right, and we see here that we have the orthogonal or perpendicular sense here, right? So that's what the geometry of this idea of orthogonality means. Right now, again, right, we can visualize this in R2, R3, right? But this concept applies to just in general Euclidean M space, right? But we just have an intuition of what that means. We don't really have a clear, like a picture of something, let's say R5, that is orthogonal, right? The calculations, although we don't need to kind of visualize it, is purely a computational check, right? Just evaluate inner products. All right, now we're gonna build on this here, and we're gonna define, well, what if a whole set was orthogonal? What does that mean, right? So here, let's define what an orthogonal set of vectors is, right? So let's look over here. I'm gonna switch over to our textbook here just to look at the definition here. Okay, so what does it mean? I know what it means for two vectors to be orthogonal, but what do we mean when we say a set of vectors? All right, so if we look at our textbook here, and we're going to define an orthogonal set of vectors. Suppose that S is equal to U1 through UN is a set of vectors from Cm, again, R to the n. We're looking at Euclidean M space. Then S is an orthogonal set if every pair of different vectors from S is orthogonal. That is, UI, inner product of UI, Uj is 0 whenever I does not equal to j. All right, we call this pairwise orthogonal, right? You just take it in pairs. Each pair that you take is orthogonal. Okay, now we can take it a step further here, and if the norm of all of the vectors there was 1, right? Every single one of them had a norm of 1, then we would call that orthonormal. All right, so here, let's just write that down here. Okay, so here, if we have set U1, U2, all the way up to UN, right, and we have U sub I and U sub j, the inner product of that is 0 for I not equal to j, then S is orthogonal set. Now, in addition to S being orthogonal, if I add the extra condition that now if it so happens that the norm of U sub I is equal to 1 for all I less than or equal to n greater than or equal to 1, right? So in other words, the length of each one of those is 1, then S is orthonormal set. Okay? All right. So that is the definition of both of those cases. And we'll see in a minute why that is advantageous here, right? Now I want to go back to those vectors that I did in R2 to just show a quick calculation of what it means to be orthogonal, right? These vectors have a special name, right? These are what we call the standard unit vectors, right? Depending on if you're taking the physics or in Math 3, right, we call them I, J, and K, right? Those are the standard unit vectors. We have a slightly different notation in this. So I'm gonna, again, go over to our textbook here. Okay, and then we see here right below the definition of an orthogonal set, we define the standard unit vectors, which we call E sub j, right? Being in C to the m, right? But again, Euclidean m space here now. What all this means, this piecewise notation means, is that if I'm looking at E1, right, then it's 1 at the first, it's 1 in the first, excuse me, 1 in the first entry and 0 everywhere else. Okay, so here let's write that out here and then have a, so we're clear when we're talking about standard unit vectors, what I am referring to. So you got standard unit vectors. All right, so let's say we had E1 to E sub m, right, in R to the m, right? So we have the entry E sub I. So what that notation that we saw from the book is that it's 1 in the ith entry and then 0 everywhere else. Okay, so let's say we were in R2, right? So R2 is going to have 2 standard unit vectors, which we call E1 and E2. Okay, and these look like this: 1, 0, 0, 1, and R sub 2, R2. Okay, and similarly in R5, this is going to have 5 standard unit vectors. Okay, notice we use the same, right, letters, same notation, right? So it's important to realize when we're referring to these standard unit vectors that we are specific as to what space we are dealing with, right? Because here E1 and R5 looks like this. And then E2, we got 0, 1, 5, and E3, 0, 0, 1, E4, oops, and then lastly, E5 is, all right, okay. So those are the standard unit vectors. You can easily verify that this is an orthogonal set and actually orthonormal as well. Okay. All right. So now we have a. So I want to introduce a theorem here, which is a nice consequence of this orthogonal set that gets us, well, let me introduce it and then we'll kind of discuss what the consequences of this being a theorem are here. So let's take a look when we're looking at theorem. Let me switch over here. Okay. All right, so we're looking at theorem OSLI. So we said, suppose that S is an orthogonal set of non-zero vectors. Okay, important, right? Non-zero. Then S is linearly independent. Okay, all right, and it makes sense that it has to be non-zero, and we'll see why that. Setting that as my hypothesis and requiring the set to not include zero vectors, what the result gives me. So let's actually prove this, right? So I'll go over the proof here. I find this proof to be not as descriptive as I would have liked, but so let's switch over here. Okay. So we have theorem OSLI. Okay, and we'll start with let S be equal to U1, U2, and U sub n. Okay, and they are in R to the M and non-zero. So, sorry, the hypothesis where S is orthogonal, 0, and S is an orthogonal set. Okay, now again, we make this distinction of they're non-zero, right? We can think the zero vector, just by the nature of the inner product, is going to be orthogonal to every vector, right? So that's one thing to keep in mind there. Okay, so here we are specifically looking at an orthogonal set where none of them are the zero vector. Okay, so we want to prove that S must be Li, linearly independent. So again, when always you're asked to show or prove that something is linearly independent, let's start off by setting up our linear dependence relation, which is this equation. Excuse me. Okay. So what I'm going to do here, so this is my linear relation here. What I'm going to do is I'm going to take this linear dependence relation and I'm going to take the inner product of u sub I, right? Just any vector, right? So this is going to work for each u sub I. Take the inner product of u sub I with the vector on the left side here of my linear dependence relation and on the right side here. Right, so for each u sub I for I ranging from n, from 1 to n, all right, so I'm going to take the inner product of u sub I with that whole vector there, alpha 1, u1, that's alpha 2, u2, alpha sub I, u sub I, again, just a general, like it's going to be all of them, right? u1 through un, just each. We're just doing them all at once here, but think of doing this n number of times for each vector, and you'll see the result that we're going to get. All right. Now here, excuse me, using properties of the inner product, this one here is going to be 0. Okay. Remember that 0 vector is just a column vector made up of all zeros. So when I multiply with each entry of u sub I, which it again is not the 0 vector, so it does have some non-zero entries, but when you multiply those by 0, they'll all go to 0. And here applying properties of the inner product. So by applying properties, so I can split it across the sum, and I can factor out the scalars, alpha 1, alpha 2, all the way to alpha n. So I can write this as alpha 1 ui u1 plus alpha 2 ui u2 plus alpha I ui ui alpha n ui un. Okay. Plus. All right. Now we're going to bring in our assumptions that I had to begin this this theorem here, right? So the set S was orthogonal, so that means that all of these are going to be 0. All of them except this one here. All right, this one. So here we made this step, right, by assumption that S was an orthogonal set. Okay. Now, we're left with this equation here. Now, here's where is our other assumption, right? We said all vectors were non-zero vectors. So u sub I is not a 0 vector. So that means that this quantity is strictly greater than 0, right? Again, also properties of the inner product, right? It's greater than or equal to 0, but 0 only when the vector is the 0 vector, but by assumption it is not. So I gotta be more rigorous here with labeling my vectors here. Right, so that's strictly greater than 0, so the only way that happens is when alpha I is 0, right? And again, what is I? I can repeat this operation for 1 all the way to the n. So what that tells me here, in conclusion, is that alpha 1 equals to alpha 2 equals to alpha 3, etc. Alpha n is equal to 0. In other words, S is a linearly independent set because only the trivial solution is possible, right? Now this brings up a kind of a bigger result of orthogonality, that if a set is orthogonal, right, we automatically get linear independence. So I don't even need to check that, right? If I can check that they're orthogonal, right, a quick inner product check, and they are orthogonal, then this theorem tells me that they're automatically linearly independent, right? So linearly independent is a result of orthogonality, which is a nice thing to have, right? To know that if you can show they're orthogonal, you know they're linearly independent. Okay, so let's look at an example here, right? To show, let's say we're given a set S. We're given 3 vectors. We'll call them U1, U2, U3. Okay, and the vectors are defined as 1, 1, 0, 1, negative 1, 1, 1, negative 1, 2. Okay, and I want to show and ask, is S orthogonal? Okay, so the way you check this is you just pairwise U1, U2, U2, U3, and U1, U3. These are all the possible combinations. Remember, U2, U1 is the same as U1, U2. Okay, so if we do this, U1, U2, that would be 1 times 1 plus 1 times negative 1 plus 0 times 1. So we get 0 times 1. So that equals to 1 minus 1, which is equal to 0. Excuse me. Okay. Now, if at any point one of these inner products is non-zero, you can stop there and the S and the set will not be orthogonal. But we'll keep going with the absence of that. So we get 1 times 1 plus negative 1 times negative 1 plus 2 times 1. So we get equals to 1 minus 1, plus 1 sorry, this one is minus 2. Minus 2. So we get 1 plus 1 minus 2, which gives me 0. And then lastly, our last set here is U1, U3. So we get 1 times 1 plus 1 times negative 1 plus 0 times negative 2. And then this gives me 1 minus 1, which is equal to 0. Okay, so is S orthogonal? Yes. Not only that, the previous theorem tells me that not only is S orthogonal, it is also linearly independent as a result. All right, and not only that, we have three vectors in R3 that are linearly independent. So it also spans the space R3. All right, so a nice result here of we see an orthogonal sets, how much information we get. Right? Now, the next question is, so can we build an orthogonal set, right? I can give you one and you can check whether it's orthogonal, right? But can I actually build one essentially from scratch, right? And that is what the Gram-Schmidt procedure is, which we will go over in detail in the next video.